Good afternoon. So, dear colleagues, young and old, dear students, dear guests, ladies and gentlemen, on behalf of the Mathematics Center Heidelberg, and in fact all mathematicians at Heidelberg University, it's a pleasure to welcome you to this year's Emil Artin lectures here in the Mathematikon and online via Zoom. Do we have people in the Zoom in the end? We do? Okay, good, so welcome. So I should begin by communicating the regrets of Ottmar Fenn-Jakob, who is the chief organizer of this year's event. Unfortunately, he tested positive for corona a couple days ago, and so he can't be with us today. But with the speaker's permission, the lecture will be recorded, and then Ottmar and anyone else in the same situation can then watch the lecture on YouTube. Okay, so let me say a couple of words about the Emil Artin lecture. So we established some 10 years ago with the aim to dignify important developments and fundamental contributions in mathematics and present them to the academic public being interested and trained in mathematics. So they're named in honor of one of the leading algebraists and number theorists of the 20th century, Emil Artin, not because of any particular historic or personal connection with Heidelberg, but because of the enormous influence that Artin's work has had on the research at the Mathematical Institute over the years, and also because of Artin's unique style of doing mathematics that the initiators of the series wanted to take as inspiration and honor with this annual event. So just to remind you of the key dates, Emil Artin was born in 1898, correct, right? He studied there with Philipp Furtwängler and then in Leipzig with Gustav Höcklotz, where he obtained his doctorate in 1921. He went to Hamburg, where he became an ordinary professor in 1926. Then the Nazis forced him to emigrate to the United States in 1936. He first found a position there in Bloomington, Indiana, and then in 1946 in Princeton. He returned to Hamburg in 1958, where he died in 1962. So Artin, as many will know, or better than me, has made countless contributions to mathematics, especially in algebra and number theory, many topics named after Artin, but also in topology, in fact, so for example, by the invention of the braid groups. So the style that I alluded to at the beginning has been characterized by an idealistic and almost artistic conception of mathematical structure, which is reflected in Artin's lecture and also in lecture style and also in his writings. So, following the 2-year corona hiatus, this is the 9th lecture in the series. The first was in 2012, I believe. And it's a great honor and pleasure for me to introduce this year's distinguished lecturer, Professor Chandrashekar Khare. Shekhar Khare studied mathematics at Trinity College in Cambridge, then went to Caltech for his graduate studies, where he completed his PhD in 1995 under the supervision of Haruzo Hida. He worked at the Tata Institutes in Mumbai for 9 years, first as a research fellow and then as an associate professor from 2000 on. He was simultaneously associate professor at the University of Utah before moving there definitively in 2004. And since 2007, he has been professor at UCLA. Shekhar's research concerns modular forms and arithmetic geometry, and specifically modularity of Galois representations. His most noted work is the proof of the Serre conjecture in the late noughties, do we say, partly in collaboration with the French mathematician Jean-Pierre Wintenberger. Professor Khare has received numerous awards for his work, including a Scientist of the Year award of the Indian Science Academy in 1999, the Fermat Prize 2007, Guggenheim Fellowship in 2008, the Infosys Prize 2010, and the Cole Prize in Number Theory in 2011, together with Wintenberger. And in 2010, he was invited speaker as the ICM in Hyderabad again with Windenberger. So without further ado, here we'll ask him for his lecture. So the title is Modularity of Galois Representations from Ramanujan to Serre's Conjectures. Please welcome Professor Khare.
Thank you. Is this mic working fine? Or? Yeah, sure. All right, thanks so much, Johannes, for the kind introduction, and thank you everyone for coming. So in fact, I was, Gebhard Bokler, who works here, was visiting LA and asked me if I would be interested in coming to give this lecture, and I jumped at the opportunity and decided to come, though Gebhard is not here. So but it's a great pleasure to be here. In fact, I was at the Artin lecture given by Henri Darmon in 2014, so I was in the audience, so it's good to trade positions and give this talk. So my talk is going to be about this title, about Galois representation. I want to tell the story where I begin with a paper in the 1916 by Ramanujan and kind of try to trace this story. I mean, I think his paper was highly influential and has influenced number theory, and I think there's a line to be drawn between Ramanujan's work in 1916 and Andrew Wildes's solution of Fermat's last theorem in roughly 1994. So I want to talk about this kind of story, tell you the story of going from Ramanujan's observations in this 1916 paper and ending up with some work of Wiles and then follow-up of work with Jean-Pierre Vinton-Berger and myself on Serre's conjecture. So that is what I want to do in the next hour or so, tell you about these developments which happened across the 20th century and maybe also they continue now. So that's my intention. Yeah, and in some sense, to justify why it's good to give this talk, maybe as in a lecture series devoted to Artin, in some sense, Serre's conjecture, which is going to be one of the things I'm going to talk about, concerns itself with extensions of the rationals with Galois extensions, with Galois group something like GL2 of a finite field. So these are non-abelian extensions, and Serre's conjecture can be thought of as a sort of reciprocity conjecture for these non-abelian extensions. And one of Artin's celebrated works is the reciprocity law for abelian extensions of general number fields. It's supposed to be like the ultimate reciprocity law for abelian extensions, generalizing things like Gauss's quadratic reciprocity law. And Serre's conjecture is a step in the direction of trying to have non-abelian some sort of extension of Artin's work or the theorems of class field theory to non-abelian extensions of the rationals. Right? So in some sense, that is also part of this subject, non-abelian class field theory. So here's a nice picture of Artin. In fact, I was recently in Bloomington, Indiana, where I did see his picture even in the common room. He spent some time there, as Johannes told us. Okay, so that's Artin. So let me start with, so I want to talk about Ramanujan's paper, and that paper actually has a remarkable series of observations about the tau function, which is now what is now called the Ramanujan tau function. So these turn out to be coefficients of some sort of holomorphic modular form, though I don't think Ramanujan was thinking about modular forms when he was writing this paper. So the delta function had been studied extensively in the 19th century, but so it's a complex analytic function, but Ramanujan started an arithmetic study of this delta function, right? So it's a complex analytic function, so one would think that maybe it has little to do with number theory, at least at that time. People may not. Ramanujan was the first to observe, perhaps, that if you look at the coefficients of the Fourier expansion of this delta function, then it seems to have certain remarkable properties. So these coefficients are called in his honor. These are called Ramanujan's tau function. So I'm going to start from scratch by defining the delta function, or at least telling you what some of the properties are, and the tau function. And also this delta function in some sense played a key role in the initial breakthrough in my work with Jean-Pierre Vinton-Berger about Serre's conjecture. The first case of Serre's conjecture we proved was to do with the Ramanujan delta function. So I think the delta function is perhaps a good object to use for telling the story about the development of this business of arithmetic of modular forms. So looking at modular forms from an arithmetic point of view. So let me just start from scratch by telling you what modular forms are. So these are certain functions on the holomorphic functions on the Poincare upper half plane. So, and they are basically defined by this property that they're holomorphic and they're invariant under translation. So they have a Fourier series in expansion in e raised to the power of 2 pi I z, right? And then they have a more kind of subtle symmetry under Mobius inversion, right? F of minus 1 upon z is z to the k times f of z, where k is kind of called the weight of the modular form. It's going to be typically a non-negative integer. And yeah, so this is the space of, it's a complex analytic space to begin with. It turns out to be a finite dimensional space finite dimensional vector space. Okay, so what's going to be, okay, so starting with this, you can somehow see that it's invariant under Mobius transformation. It has some transformation properties under the action of SL2Z on the upper half plane under Mobius fractional linear transformation. So f of az plus b upon cz plus d is equal to cz plus d to the k times f of z, right, for all 2 by 2 matrices with integral coefficients and determinant 1. And within this space of modular forms, there's typically a codimension 1 subspace given by the vanishing of the constant term, the a0. In the Fourier coefficient, you could demand that a0 is equal to 0. So now it turns out that it's not hard to see that the space of modular forms of weight k is 0 unless k is a positive even integer, or non-negative even integer. So this evenness is kind of part of this subject. There's some sort of parity thing which comes in. And okay, and so this space is non-zero for all even integers bigger than or equal to 4. Right? So we have this complex vector space which has these sort of properties that there is a certain non-vanishing property for odd k, and for even k it's a non-empty space as long as the weight is at least 4. So there's sometimes you can, because these functions have some symmetry, you can try and write down some sort of examples of these forms by performing some symmetric kind of symmetrizing certain sort of functions. So you can write down a nice example of a modular form. This is called the kth Eisenstein series of weight k. Right? So this exists whenever k is at least 4 and even. And it has this nice Fourier expansion where the constant term is somewhat mysterious. It's related to zeta functions evaluated at negative odd integers. And the non-constant coefficients are some simple arithmetic functions. It's sigma k minus 1 of n, where this is just the sum of divisors functions of n raised to the power of k minus 1. Right? So we have this kind of explicit modular form, which we can write down for all weights, except that these are not cusp forms. Right? So this I should have said that the space of modular forms whose constant term is 0, so vanishing at infinity, is called the space of cusp forms. So this is an example of a modular form of weight k, which is not a cusp form, because the constant term actually is very interesting, while the other terms are perhaps more explicit and elementary. Right? So somehow that's something you can write down. And I've defined the kth Bernoulli number, right? They show up in various contexts. Okay, right? So this is the space of modular forms of weight k. I've written down an example. And in Ramanujan's paper, typically great attention is paid to two particular weights, 4 and 6. So then you have these modular forms, the Eisenstein series of weight 4 and 6, which have this explicit form, right? You know. And they were called Q and R by Ramanujan in this paper, right? So in general, and we also have this decomposition that Mk is a space is spanned by the Eisenstein series. So this is just this explicit modular form we can write down. And then the complement is the space of cusp forms, right? And this modular forms kind of start existing when k is bigger than or equal to 4. Cusp forms have a harder time existing, so they start, they're not 0 unless for a larger range of weights. And okay, so the first non-zero cusp form is the form which is going to be called the delta function, right? Up to scaling. So we consider the entire algebra of modular forms, right? You consider modular forms of a fixed level, which is level 1. You're looking at the entire group SL2Z, and you look at all weights, and you look at the direct sum of modular forms of weight k. So this is a graded algebra. You can multiply 2 modular forms, you can get another modular form, and the weights add up. And it turns out, and all this, of course, if you want to reference, this is there in Serre's course in arithmetic in the last part of the book. So this is a graded algebra, and it's a polynomial algebra in these 2 particular modular forms, which Ramanujan called Q and R, E4 and E6. And these are weights 4 and 6. And so now we are just, so far we are just doing complex analysis, right? Though we've already seen that the Fourier coefficients of these Eisenstein series already have some arithmetic meaning or significance. And so just now these modular forms are just complex vector spaces of finite dimension. And using some sort of algebraic geometric interpretation of them, you can write down their dimension, right? Roughly the dimension is k by 12. On the other hand, I mean, the space of cusp forms, somehow it's hard to write down explicitly, though you can for things coming from sort of theta series and so on, but it's hard to write down explicitly modular forms which are cusp forms. And the space of cusp forms vanishes for a larger range of weights up to weight 10, right? And the first time you have a non-zero cusp form is in weight 12, and whenever something happens for the first time, it's interesting, right? So this delta function is the first, is the weight of is the modular form at weight 12, and weight 12 is the smallest weight at which you have a cusp form, right? And that's a one-dimensional space, and up to scaling, you can normalize it so that the first Fourier coefficient is 1, A1 is 1, and you get the delta function, right? So this is though Ramanujan, I don't think, was thinking about modular forms when he was writing his paper. But the delta function, though it's nowadays called the Ramanujan delta function, but of course it was studied classically before Ramanujan. It was studied in the 19th century in the context of elliptic curves. It is related to the discriminant of elliptic curves, and is thus classically an important form on the space of on the moduli space of elliptic curves. But what makes it a part of Ramanujan's legacy is the fact that he really started a very arithmetic study of its Fourier coefficients. Right? And somehow in Ramanujan's case, story, of course, he was very fond of numbers, as is told. And there are two numbers which occur in his biography, 1729, right, and 691. So this is, some of these numbers show up in Ramanujan's study of the delta function. We'll see how 691 shows up. 1729 has another significance. Okay, so this modular form is explicitly defined in terms of as a polynomial in Q and R, as somehow is related to how it shows up as a discriminant function coming from elliptic curves. And it has this explicit kind of Q product expansion. Q times product of 1 minus Qn to the 24, right? So in some sense, Ramanujan was perhaps looking at this definition of the delta function. It's just an explicit sort of, it has this product expansion. And then you write down its Fourier, write it down as a Fourier series, and then it has this form of being of summation tau n q to the n, right? So just by definition. The tau n are just the definition, are the Fourier coefficients of this particular cusp form of weight 12, the smallest weight at which you have a cusp form for this full modular group. Okay, and then Ramanujan in this paper, in 1916, conjectured three remarkable properties of this Ramanujan, of this tau function. He conjectured that tau is multiplicative, not completely, but tau mn is tau m times tau n when mn are co-prime integers. Then he also conjectured a recursion formula for values of tau at powers of p, right? Tau p to the n plus 1 is not totally multiplicative. There's tau p to the n times tau p, and then there's a correction term minus p to the 11 times tau of p minus 1, n minus 1, right? And then he also conjectured this remarkable Archimedean property of tau p, that the absolute value of tau p, it's just from its description, you see it's a rational integer, but its size, he conjectured, should be 2 times p to the 5.5, right? 2 to the p times 11 by 2. Any questions so far? Okay, so in Ramanujan's 1916 paper, you find this table of tau n, right? So he writes the tau n down for n from n equal to 1 to 30. Of course, tau 1 is easy. As you see, it becomes rapidly quite big. Right? Tau n is, okay. So you find this in his paper. And then on the basis of these, maybe I'm sure he may have computed more in his head or maybe scratch paper, but just looking at these values, he kind of conjectured these three properties which I wrote down, right? These properties of how tau behaves with respect to the factorization of n, and then this last property, which in fact turned out to be the deepest property, right? Hardest property to prove. Okay, so he he was around, how old was he around? 29 when he made these conjectures, okay, and died not soon thereafter. Okay. So yeah, but these conjectures were turned out to be very highly influential for the course of number theory in the 20th century. So let me tell you how they kind of influenced. So the first two statements were proved by Mordell soon after Ramanujan conjectured them, right? So the first two statements it didn't take long to be proved. And they were proved as a consequence of endowing the space of modular forms with more structure, right? Mordell defined certain operators, which are now called Hecke operators. He defined operators T sub n for each value of n, integer, and they commute with each other, and they preserve some sort of inner product, the Peterson inner product, and they're Hermitian operators with respect to this inner form, and they can be diagonalized, right? And these operators somehow have group theoretic meaning, right? So they're operators. And because they have some meaning, one can prove these properties which Ramanujan conjectured for the tau function instead for these operators. Right? So it turns out that these Hecke operators, they act upon the space of modular forms of weight k, preserving the space of cusp forms, and they in turn satisfy tau mn is tmn is equal to tm times tn for coprime mnn, and the same recursion formula for t evaluated powers of p as the Ramanujan delta function was supposed, as the Ramanujan tau function was supposed to satisfy. Okay, so furthermore, the connection between Fourier coefficients and the Hecke operators is if you do have an eigenform for the Hecke operators, and then the first Fourier coefficient always turns out to be non-zero, and if you normalize it to be 1 by scaling it, then there's an intimate connection between the eigenvalues of the nth Hecke operator and the Fourier coefficients, right? F of Tn turns out then to be an times f. Right, so basically there's a connection between Fourier coefficients and of an eigenform for the Hecke operators and the eigenvalues of f of this operator, right? And it turns out these Eisenstein series with these explicit modular forms I wrote down, they are indeed eigenforms for Tn with this very simple eigenvalues, right? These simple arithmetic functions, sigma k minus 1n. Okay, so there's, so those of you who've seen it, okay, there's an explicit formula for what the Lth Hecke operator does to the Fourier expansion of f, okay? And it turns out, it turns out that because delta is a unique cusp form of weight 12 up to scaling, and it is forced to be an eigenform for the Hecke operators, right? So it turns out that delta z, when you apply TL, and because delta is normalized, the normalized form with the first Fourier coefficient equal to 1, the Fourier coefficient, the tau L turn out to have an interpretation as eigenvalues for these Hecke operators TL, right? So because model had proved, because these operators have meaning, unlike if you just think of tau L as tau n as appearing combinatorially as kind of from some generating function, these Hecke operators have more meaning, and you can then prove properties of these Hecke operators, which Ramanujan had conjectured for tau, right? Because of their having more structure. And because these tau n's are eigenvalues for the Tn's, model deduced that the tau n satisfy the properties, the first two properties conjectured by Ramanujan. Right? So somehow you have to endow the space with more structure, and then you can somehow see, Ramanujan's conjecture coming out. Right, so this is what we nowadays one might fashionably call categorification. Rather than dealing with numbers, you interpret them as eigenvalues of operators. Right, the operators have more meaning, and hence you can prove more things about them, and then deduce things for the eigenvalues. Right, so instead of viewing tau n as just given by this combinatorial kind of expansion, you recognize that actually this product expansion is actually a cusp form, and then you define operators on spaces of cusp forms and realize tau n as eigenvalues of these operators. You can prove some things about the operators and hence deduce the same for the eigenvalues. Right? So that's how model rather quickly, within a few months, I think, of Ramanujan's conjecture, of the first two conjectures, proved the properties of tau n. Okay, also what is remarkable about the Ramanujan's paper is that this is the first time, I think he wrote this down, this is the first time in the history that there shows up a L function, right, which has an Euler product expansion of so-called degree 2. Right, he showed that these properties conjectured by Ramanujan for tau mn and tau p to the n, they can just be formally interpreted as the fact that if you look at the L series from delta, summation tau n upon n to the s, right, that has an Euler product of expansion with Euler factors of this shape, right? 1 minus tau p to the p minus s plus p to the 11 being 12 minus 1, where delta is the modular form of weight 12, right? Or 11 minus 2s. Okay, so and then Hecke proved that the completed L function, where if you kind of complete it at infinity, has a functional equation of the form lambda 12 minus s is equal to lambda s as a consequence of the subtler property of modular forms that they are invariant they have some transformation property under the Mobius inversion. Right? So this is in some sense the first time in the literature that you have a L function which has an Euler product expansion of degree 2. In the sense, if you call x somehow, if you denote p to the minus x s by x, then somehow if you look at this Euler factor, it looks like 1 minus tau p x plus p to the 11 times x squared. Right? The Euler product expansions of degree 1 had shown up, of course, in the zeta function, in the Riemann zeta function and Dirichlet's L function. Right? But this is the first time, because those are kind of GL1 objects. This is really a GL2 object, right? Coming from some SL2's head symmetry. Okay, so these papers, already the observations of Ramanujan kind of generated some new mathematics, and okay, they had this interpretation in terms of L functions. Now the last property, Ramanujan conjecture, which is this bound on the size of tau p, right? He conjectured that tau p is less than or equal to 2 times p to the 11 upon 2. Right, so that took many years to prove. It took like decades, 6 decades or something to prove, and it was proved by Delhi only in the early 1970s after his proof of the wave conjectures. Right, and this bound is actually remarkable because, I mean, if you just look at the values of tau n or tau p, right, it's not clear why one would conjecture something like p to the 5.5. Right, the kind of weaker bound of p to the 6 is actually very easy to prove. Right, it's just a consequence of the maximum modulus principle in complex analysis. Right, you can find a proof in various places. So in fact, when Hardy gave, I think, his 12 lectures on Ramanujan, he was very skeptical about the not very, but he was slightly skeptical about the importance of the sharpening that Ramanujan had conjectured from 6 to 5.5, right? So it's some kind of power saving, as people call it nowadays. So he said that we seem to have drifted into one of the backwaters of mathematics. Right? But though he qualified this by saying that because Ramanujan is saying this, that it might have some features which made it not unworthy of Ramanujan's attention. But of course, it turns out that this conjecture is like a master conjecture, which is kind of a conjecture which is you can make for all kinds of automorphic forms, and very few cases of this are known. This particular case was proven, but after 60 years, and it has turned out to be one of the kind of important things to try and prove about in the context of automorphic forms. Right? Any questions so far? Okay, now so these were the observations of Ramanujan. There was also another kind of thing he observed, again in that same paper. He observed this remarkable congruence for tau n, that tau n is congruent to sigma 11n, so the sum of divisors function of n to the 11th power, mod 691. Now the number 691 somehow shows up here because it is the numerator of the 12th Bernoulli number. Right, and these sigma 11n are the Fourier coefficients of the 12th Eisenstein series of weight 12. Right, so somehow he saw that there was a congruence mod 691 between the Ramanujan delta function and this much simpler modular form of weight 12, which is the Eisenstein series. Right, so this was yet another observation he made in that same paper. Okay, so so this in some sense is the congruence which really influenced the series of developments which I want to talk about, which led Serre and Swinnett and Dyer in the 1960s to try and understand this congruence and why certain congruences existed, modular certain primes, but not other primes. It led to the theory of modular forms, led to various things. Okay, so I'm going to focus on this kind of congruence. So there were others following him. Many people thought about these congruences for the Ramanujan tau function, English mathematicians, Indian mathematicians, and such. Many congruences were discovered modulo a specific set of primes, 2, 3, 5, 7, 23, and 691. Right, so people found congruences modulo such primes. So these are now called exceptional primes for the Ramanujan delta function. Now the feature of these congruences is that the tau n has no closed formula, right? You can't really write down what tau n exactly is. But modulo these primes, somehow tau n simplifies. There's some explicit formula for it. Like mod 691, it is just sum of divisors functions to the 11th power. Okay, so now some of these numbers, okay, there were these congruences sitting, people had just observed them. They're not very hard to prove once you kind of observe that something like this should exist. But people didn't have a theory about why these congruences exist, why people had never found congruences in spite of looking for any other primes. Right? So there was this sort of thing around, and then in the 1960s, starting in the late 60s perhaps, Serre and Swinnett and Dyer started investigating more thoroughly and deeply these congruences. And also at the same time the Ramanujan Brown. So the explanation for these congruences actually lies in yet another interpretation of these tau functions, perhaps in a slightly more sophisticated way, as something to do with Galois theory. Right? Again, maybe Emil Artin, okay, certainly did a lot of stuff in Galois theory. Okay, so the explanation kind of for congruences and the proof of Delin of Ramanujan's third conjecture, which is about these Ramanujan bounds, would lay in the kind of different kind of interpretation of the Ramanujan tau function via Galois representations. Right, so somehow, so let GQ be the absolute Galois group of Q. So it's the Galois group of Q bar over Q, of an algebraic closure of Q over Q. Right, so it's a huge group, very mysterious. One knows very little about it. One of the basic theorems of Artin, I think Artin Schreier, is that you can classify at least the torsion elements of this group, GQ, right, the identity and the class of complex conjugation, conjugacy class of complex conjugation. Okay, so it's a mysterious group, and somehow people think that it controls a lot of number theory. So, Serre conjectured around 1967 in an article he's published in the seminar Delange Piso-Portu in 1967-68. He conjectured that should exist a representation, right, of the absolute Galois group of Q into GL2 of the L-adic numbers, right? GL is just the inverse limit of Z mod L to the n, so it kind of captures all kinds of congruences mod L powers of L. Ramanujan conjecture the Serre conjecture there should exist the L-adic representation of this absolute Galois group of Q, two-dimensional, somehow related to the fact that we are dealing with modular forms and hence they have some symmetry under two by two matrices. And this representation is characterized by the property that the characteristic polynomial of certain marked conjugacy classes in this Galois group, right, which are called Frobenius elements, Frobenius at P, right, this Galois group has certain sort of marked elements, like Frobenius at infinity is complex conjugation. So Frobenius at P for finite primes P should, so somehow the interpretation of now tau P is going to be as traces of certain elements arising in this Galois representation. Right, so the representation is characterized by the property that the characteristic polynomial of rho delta L of Frobenius at P, right, which is some element in this Galois group which is responsible for raising things to the pth power, for all primes P not equal to L is x squared, is this Euler factor at P, right, is this Hecker polynomial at P. So x squared minus tau Px plus P to the 11. Right, so now the del tau function gets, so this conjecture was of course not out of the blue, right? Somehow for weight 2 modular forms, this was a classically known theorem of Eichler and Shimura. Eigenforms for Hecke operators in weight 2 already had a Galois theoretic interpretation. In fact, Eichler wrote down such a construction and studied these properties for x0 11, and then Shimura generalized it for arbitrary x0 n or x1n, but weight 2. Right, so somehow Serre was conjecturing that the same kind of Galois interpretation of modular forms via Galois representations should exist for higher weights. So it was kind of reasonable perhaps to expect. So now here's another example of categorification, right? Rather than looking at numbers, sequence of numbers tau P, okay, you've already realized them as eigenvalues of operators, right? Now you're kind of giving them maybe a higher interpretation as traces of Frobenius in certain sort of more complicated things like Galois representations. Okay, and somehow this turned out to be the key for Deline's proof of the Ramanujan's conjectures for the size of tau P. Right, so these representations somehow, soon after Serre conjectured them, again it took maybe, I don't know exactly, but maybe within a year or two, or maybe Deline, and I think in a seminar Bourbaki wrote down a construction of these Galois representations. Right, so and they occur in some étale cohomology just of the J line of some kind of local system, right? So he interpreted them as arising in some geometric way. These Galois representations were realized in étale cohomology, right, this tau P now turn out to be the trace of Frobenius at P acting on this cohomology group, and then he proved later on, after 5-6 years, he proved the way bounds, way conjectures, and thus deduced the Ramanujan conjecture as a consequence of this very elaborate theory. First, you have to construct these. Now realize these numbers as coming from étale cohomology and then prove the way conjectures for bounds and eigenvalues of Frobenius acting upon étale cohomology of smooth projective varieties over Fp or something. Right? So this was this rather very elaborate story which took many, many decades to realize. Right? So this is the proof of Ramanujan's conjecture. This last conjecture took some proving. Okay? Any questions for anything? So. Yes.
So this is sharp. You can't make any better one.
Yeah, I think this is pretty sharp. Yeah, there are these. Yeah. Yes. There are also these Sarto-Tate conjectures which tell you somehow that these. Yeah.
How it saturates this one.
Yeah, I think it does. Okay, so now this is how the last of Ramanujan's conjectures got proven. But then Serre and Sunet and Dyer also started trying to analyze what are these Galois representations? What are their images, for example? Right. So Serre, in that same article in his this Delange Piso-Portu seminar, had showed that the existence of these L-adic Galois representations, which at that time he just conjectured to exist, right? He hadn't proven them. But no matter, without even knowing they existed, Serre and Sunet and Dyer started studying what properties these Galois representations should have. Right? For example, one of the things which convinced Serre that the Galois representation should exist, right, was that somehow Serre and Swinnett and Dyer showed that the existence of the two-adic Galois representation and properties of that could explain some rather intricate congruence modulo 2 to the 11 that Lehmer had found for the Ramanujan tau function. Right? So this particular congruence could be explained by saying that the image of the two-adic representation which Serre had conjectured to exist should have index 3 times 2 to the 25. Right? So somehow there was this kind of verification in some ways of, or at least convince the fact that this Galois representation, because if you have a Galois representation, you're asserting something rather strong. Right? You're making all these tau p's appear as elements of Frobenius of some rather small kind of group. So there's a lot of relations between these tau p's, right? And so somehow one is putting a lot of constraints, and the fact that this congruence could be explained maybe made Serre think it's reasonable that this Galois representation exists. Of course, Deligne proved it existed shortly thereafter. Okay, so now what is, for example, the Galois theoretic meaning of the congruence of tau and mod 691, right? So in terms of the Galois theory, in terms of the mod 691 representation of associated to this associated with delta, one can just say that the Galois representation somehow degenerates, right? It becomes reducible, or it is reducible, mod 691, and it is of this form up to semi-simplification. It is a direct sum of the identity character and the 11th power of the mod 691 cyclotomic character, right? Which observes the action of GQ, of the absolute Galois group of Q, on 691st roots of unity, right? So somehow this was the kind of in terms of images. So it's the images of the Galois representation associated to this delta function, let's say mod L, mod 691, can explain congruences, right? So somehow that was one idea of, that was somehow the idea of Serre's, Serre and Swinnett-Dyer's theory to interpret Ramanujan's congruences and to look at them via Galois theory. Okay, so now, as I said, even before perhaps Deligne proved the existence, one could just axiomatically assume these Galois representations exist, right, and try to determine what their image is. So Serre and Swinnett-Dyer, this very beautiful analysis they did in the late 60s and early 70s, that proved that these representations, rho delta L, right, these L-adic representations into GL2 of L-adic numbers, have large images, right? So they proved that that the image of this Galois representation for L not equal to these exceptional primes has large image. It contains all of SL2ZL, right? And a key step, okay, they proved some group theoretical lemma, which I'll skip here. Okay. I'm going to skip these two slides as well. So somehow the key, somehow the way they proved the results about the images of these Galois representations was by kind of starting a more arithmetic study of modular forms, right? People had studied modular forms over complex numbers. But Serre and Swinnett-Dyer started a theory of mod L, studying modular forms mod L, right? And they developed this very beautiful geometric theory of mod L modular forms, right? So this is all summarized in a seminar, Bourbaki seminar of Serre from the 1970s or something, right? So he gave this very beautiful account. As he says, this is joint work with Serre and Swinnett-Dyer, and he leaves it to the reader to perform the stylistic analysis of who proved what, okay? So they never published a joint paper, but somehow this theory came out of joint investigations by Serre and Swinnett-Dyer. Okay, I'm going to skip this because there was some theory of modular forms which they used to prove these things about images of the L-adic representations associated to the delta function. And one of the things which emerged from their work was that one has to really understand congruences between modular forms. And one of the congruences they discovered, which again was very influential for the later development of this theory in the hands of Maser, Ribbit, Hida, and others, was this kind of weight shifting congruence, right? So the delta function, which is a modular form of weight 12 and level 1, actually turns out to be congruent mod 11, where 11 is like 12 minus 1, to another modular form of weight 2 and higher level, weight 2 and gamma naught 11, right? S2 gamma naught 11 corresponds to an elliptic curve. It had been studied by Eichler, and right, and this congruence can be verified by just Fermat's little theorem formally, right? You just take the 22, write it as 2 times 11, put the 11 inside mod L, right? So there's some explicit computation, manipulation can establish some congruence between product expansions, and it turns out that this thing which shows up here turns out to be a modular form of weight 2 and level 11. Okay, so this is in some sense the L equal to 11 case of another congruence Serre actually systematically proved that there is a congruence between modular forms of weight L plus 1 and level 1 and weight 2 and gamma naught level L. right? So this kind of level lowering congruence at the expense of increasing the level, right? So somehow these kind of congruences played, for example, an important role in my proof of Serre's conjecture with Jean-Pierre Mathambéger. Okay, so for example, what did Serre and Swindendijk proved that, what did they prove, or what results did they prove about this L-adic representation associated with delta function? First of all, they proved it's irreducible and odd in the sense, so in terms of the one element of GQ you know explicitly, which is complex conjugation, the image of complex conjugation is of the form 1, 0, 0, minus 1, rather than being a scalar. It has to be something like that, being an element of order 2, okay, but it's forced to be regular. Okay, and for all L not equal to these exceptional primes, the reduction of the representation mod L, right, you can look at the GL to ZL representation and reduce it mod L. You get a GL to FL representation and it turns out to be even stronger than L-adic irreducibility, even the mod L thing turns out to be irreducible. Then it has some particular property at L equal to 23, which I'll skip. And the determinant of this representation, right, again that's not hard to prove, is the 11th power of the cyclotomic, mod L cyclotomic character. Right? The cyclotomic character is the character which tells you how Galois acts on roots of unity of order L. Okay, and somehow one of the key things that they proved is that for all L not equal to these explicit set of primes, 2, 3, 5, 7, 23, 691, the image of this Galois representation is non-solvable. Right? And the non-solvability comes from the fact that the reduction mod L of the image is large. Right? It contains SL to FL, which is essentially some sort of PSL to FL is a simple group for L bigger than or equal to 5. No, simple non-abelian group. Yeah, so they kind of they determined that some of the images of these Galois representations. Right? So Serre conjectured this to exist, and then Serre and Swindendijk, using their theory of mod L modular forms, showed what the images are. Right, and somehow using this theory, they could explain the fact that no one had ever found simple congruences for tau and mod primes other than these. How many primes are there? 6 primes. Right? Because somehow the fact that the image of this Galois representation is non-solvable for L not equal to these primes forbids any simple congruence existing for tau and mod L. Right? So somehow they found a group theoretic or Galois theoretic interpretation or explanation for why the congruences existed only for these primes and not for other primes. They couldn't exist, right? So you can formalize that in some lemma, which I'll kind of skip. So essentially the thing to take away is that the non-solvability of the image of the L-adic representations for L outside this finite set of primes explains why no one can ever found congruences, simple congruences for tau n outside these set of primes. Right? So some of the Galois theory, L-adic representations was the means for understanding Ramanujan's congruences and why they did not exist for most other primes. Yeah, any questions? And this time I'll genuinely stop to see if anyone has questions. Okay, now I want to come to Serre's conjecture. Right, so Serre, when he was doing all this, I mean, in the 1973, he started kind of conjecturing the converse to his earlier conjecture. So he had conjectured that starting with delta, or starting with, in general, he started with the modular form, let's say of level 1, he conjectured that there exists some Galois theoretic object, right, a GL to FL representation or GL to ZL representation. So now he started asking himself, in fact, the conjecture was first formulated by a letter of Serre to Tate in 1973, whether, in fact, any two-dimensional Galois representation which is odd and irreducible, as I'll come to later, should come from modular forms. So, but let me again tie the story down to delta. So if you denote K delta L, the extension which the rho bar delta L cuts out, right, which is some fixed field of the kernel of this representation. So it's typically it's some GL2 FL representation of Q. What properties does this have? It is unramified outside L and infinity. The Galois group has something to do with GL2 FL, right? And for L not equal to these primes, you get the image contains SL2 FL, right? The determinant of there's some oddness condition, so somehow this extension cannot be totally real, right? Or more, the determinant of the matrix of complex conjugation is -1. And so, okay, so now we've pinned down, somehow we are looking at this extension, which is some non-abelian Galois extension of Q, and we are just talking about it purely in terms of the image of Galois, or rather the Galois group, and some local properties of this extension, right? So some oddness at infinity, unramified at primes not equal to L, right? And at L, then one has to somehow further say what exactly the ramification is, right? So somehow the ramification is of this sort, the semi-simplification of the image of inertia at L in this Galois group, when viewed as like the Galois group as 2 by 2 matrices, right? It has a particular shape which ties it down to coming from delta, right? It's either up to semi-simplification is either 1 plus the 11th mod L cyclotomic character of the 11th power, or some other case which typically happens very little, right, as I'll tell you in my next slide. So anyway, the kind of what one can take away from this is that you have this extension and you're somehow you don't know much about this extension except you know local properties of this representation. It's unramified outside L, and at L, the ramification is supposed to have a certain behavior. Right, at that time when Serre started thinking about this in 1973, he did not know how to prove such things, right? But okay, but I'm maybe being ahistoric and saying it like this. So okay, so this part, I mean, the first behavior, which is the image of inertia is basically a sum of identity plus some cyclotomic character to the 11 is what typically happens, right? So this happens whenever tau L is not congruent to 0 mod L. Right, so one is equivalent by results of Deline and Fontaine, which were proved in the 70s under stimulation of Serre, because Serre asked these questions, to asking that L does not divide tau L. Right, so somehow this is a condition it's a condition which one doesn't know whether it happens infinitely often or does not happen infinitely often. Right, so it's kind of some condition which one expects to be generically true, but very hard to prove. Right, so this is a generic condition, and in fact, for all primes less than it holds for all primes less than 7 million and, 7 million? Yeah. Okay. The only solutions for up to 10 to the 10 to the equation tau L congruent to 0 mod L are these exceptional primes 2, 3, 5, 7, 24, 11, and then there's mind-bogglingly large prime, okay, 7 billion something or the other, right? So these are the primes up to, apparently, this I got from looking at Wikipedia, okay? So, I mean, I don't personally know the properties of the tau L function, okay? But it's also conjecture, right? So now somehow a lot is known about Ramanujan tau function, but even some basic properties are not known, in spite of all these sophisticated interpretations of the tau L function as traces of Frobenius, eigenvalues of Hecke operators. So one does not know that tau, I mean, Lehmann has conjectured that tau n never vanishes, right? This is not known. Of course, this kind of thing is known outside a density. One knows that it can vanish only for a density 0 set of primes. Okay, yeah, so somehow this is something you don't know about the tau function. But the tau L congruent to 0 mod L question, again, is, yeah, it's kind of mysterious. Okay, so in this context, as I said, Serre made these conjectures. In a rough version of Serre's conjecture would ask that any extension which is a Galois extension of Q with Galois group roughly like something like GL2FL, and which satisfies the basic ramification properties, which I stated for the extension coming from the Ramanujan delta function, should come from the Ramanujan delta function. Right? So somehow Serre started conjecturing the converse property to what he had, to things which arose from the delta function. And in fact, in my work with Jean-Pierre Mathieu, this was one of the first cases we proved that if you have an extension which satisfies these basic properties, which are these properties which I listed here, right? Basically unramified outside L, GL2FL extension, and unramified outside L, and some ramification behavior at L, it should come from the Ramanujan delta function, right? And in 2004, in the fall of 2004, when we started working on this, or when we had some initial breakthrough, this was the first case we proved of Serre's conjecture. Okay, so there's a nice picture of Serre. Okay. Okay, so in fact, so there's nothing very special about delta. I'm just focusing on delta. You can talk about modular forms of all weights in level 1, or you can even drop the question, restriction of level 1. Right? So if we drop 5, which is the exact nature of the ramification at L, then you can say that any extension with these other properties should come from a modular form, eigenform for the Hecke operators, of level 1 and some unspecified weight. Right? And when we drop the condition of being unramified outside L, then the conjecture would predict that rho k arises from a new form of some weight and level, right? So this is, so for example, how do you fit this in? I mean, let's again look at the prime L equal to 11 and think about this congruence I wrote down between the delta function and some explicit modular form of weight 2 and level 11. For L equal to 11, right? If we have an irreducible, so what does this conjecture say in this particular case? If we Serre's conjecture. If we have an irreducible odd representation of the absolute Galois group of Q into GL2F11, unramified outside 11, right? And satisfying the conditions on inertia, something to do with how inertia looks at 11, then Serre's conjecture predicts, and the congruence I wrote down, this manipulation using Fermat's little theorem, predicts that rho arises from the Levin torsion of this elliptic curve of the smallest conductor, Levin. Otherwise, for conductor less than Levin, there's no curve, there's no elliptic curve. And this is some explicit curve, right? Which is the up to isogeny. There are two elliptic curves of conductor 11 up to isomorphism, and both of them are isogenous by a phi of isogeny. This is one of them, x0 11 and x1 11. So the Ramanujan delta function is significant in another way, okay, in an unrelated way. Okay, so it also gives rise to the smallest rank 2 motive over Q with good reduction everywhere. Okay, I'll just leave it at that. Just here, size, one is the smallestness is I'm talking about it in terms of the weights, right? The Hodge weights, the Hodge type is 11, 0, and 0, 11. Okay, so I just wanted to tie down this Ramanujan thing to this congruence of Swinnett and Dyer had remarked upon, that mod 11, the representation should not only come from delta, but it should also come from this elliptic curve, which had been studied by Shimura in a paper in around the same time, late 1960s, and he had determined images of the Galois representations coming from this curve. Okay, so stated more formally, Serre's modularity conjecture asserts that a continuous, right? Any representations are going to be, any sensible representation is continuous in the sense it's going to be factored through the extension of a Galois group of a finite extension. So any irreducible odd representation of the absolute Galois group of Q into GL2 of a finite field, right, arises from a new form, right, via some construction of Eichler, Shimura, and Deligne. In other words, this abstract representation, right, we are looking at some abstract representation of the absolute Galois group of Q, actually it comes from a much more concrete object like a modular form. Right? It should be the reduction of the L-adic representation associated to a modular form of some weight and length. Okay, so that's Serre's conjecture. So he started making these conjectures in 1973, and then it was formulated some version in the level 1 case in 1975, and then made the conjecture very precise in 1987 in a paper published in Due, right? So these modular forms are supposed to be, these Galois representations come from a specific space of modular forms, right, of weight k rho and level n rho, right? So these weight and level are tied to the ramification properties of this Galois representation. So for example, the level captures the ramification properties of this representation rho for primes not equal to the residue characteristic, for Q not equal to L, and then the weight captures the ramification properties at L. Right? So for example, if you look at the Ramanujan delta function, the n rho is 1, right, and the weight is 12. So Serre formulated the conjecture in for the level 1 case for rho in a letter to Serre letter to Tate in 73, and in fact Tate in a return post or something, he proved these conjectures for L equal to 2, right, in a very remarkable but elementary argument, which turns out to be an important starting point for our proof of Serre's conjecture. So Tate immediately proved Serre's conjecture in the level 1 case for L equal to 2 by showing there does not exist any Galois representation with those properties. Right? So it was an inexistence theorem. And then he formulated in an article in 1975. And then on the other hand, in 1987, he made these conjectures precise, right? Especially in the weight aspect, in this k rho aspect. And this was partly perhaps done to make precise Frey's remarkable observation that Fermat's last theorem should follow from modularity of elliptic curves over Q. Right? So let me tell you, just mention this connection. Right? So Titaniama had this astonishing idea in the 1950s that all elliptic curves E over Q arise as quotients of x0 n. Right? And Shimura kind of made this idea more precise, and then Andre Weck really tied down the conductor and he left the proof as an exercise to the interested reader in his 1967 article. Right? So there was this, and for example, I mean, one consequence of the Weiss's precision was that one could explain some things which people already knew. Why were there no elliptic curves of conductor less than 11, as I told you earlier? Because the corresponding x0 n is of genus 0, right? x0 n has genus 0 for n less than 11. Right? So somehow when Weiss made precise the idea of the level, that kind of played a role in, that was Weiss's contribution besides these converse theorems and all that. Okay. So, so I want to have some pictures of the people who made these conjectures. So Taniama in some vague form made these conjectures, but of course it was very prophetic of him. Then Shimura kind of made more precise the conjectures, and Andre Weck, or rather he proved these conjectures for CM elliptic curves, and Andre Weck kind of made precise the level aspect. What level should it arise from? Okay. Okay, so now let me connect. How much time do I have? Yeah, I have time. So what is the conjecture? So one of the motivations for Serre perhaps to make precise these conjectures in the mid 80s was that that Frey had observed this connection, as you all know, between Fermat's last theorem and modularity of elliptic curves, right? But he had not been able to pin down exactly where the contradiction should arise. Right, so Serre kind of looked at it and made precise conjectures. Right, so the rough story is that starting with a putative counterexample to Fermat's last theorem, right? So suppose you have a solution to Fermat's last theorem which violates the conjecture Fermat's last theorem, a to the p plus b to the p plus c to the p equal to 0 with a, b, c not 0, suitably normalized. You construct the Frey elliptic curve, which I should have written down, right? So it's y squared equal to x into x minus a to the p into x plus b to the p, right? You made kind of some construction, and somehow this elliptic curve to Frey looked like something which should not exist, right? So somehow the elliptic curve doesn't exist because when you start studying the finer properties of this representation, of the mod p representation arising from this elliptic curve, right? So he looked at the mod p representation arising from the p torsion of this Frey elliptic curve, and then Serre looked at this representation and it showed that the invariants he was defining were of the weight and level were 2 in this case, right? Thus, the Serre conjecture predicts that rho arises from S2 gamma 0 2. On the other hand, x0 2 is the projective line, so there is no holomorphic form there, right? So S2 gamma 0 2 is 0, which is a contradiction, right? So starting from a counterexample to Fermat, you route it to some space of modular form which is 0, and hence the counterexample could not arise. But what Ribet did in his celebrated work in the late 80s or early 90s was, or I think he published it in 1990. He proved enough of Serre's conjecture to actually deduce the needed assertion from the basic conjecture about modularity of elliptic curves. You didn't have to prove all of Serre's conjecture. He proved enough to say that, okay, that if you just prove modularity of elliptic curves, then you're done, right? Just prove, okay. So but that took a lot of proving, right? So Andrew Wiles, in his astonishing work in 1994, proved this statement of modularity of semi-stable elliptic curves over Q. Wiles in another paper joint with Taylor-Wiles. Okay, so this was this connection between Serre's conjecture and Fermat's last theorem. Serre was stimulated, just as André Weil made precise which conductor the elliptic curves come from. Serre kind of made precise the invariance from which a given Galois representation should arise, right? And somehow this precision is important because you need it to, for example, deduce Fermat's last theorem. Okay, so now what about, Van Tomberg and I proved Serre's conjecture roughly in the period 2004 to 2009, which is to say that we started in 2004 and the papers were published in 2009. So our proof, for example, gave a way of directly proving Fermat's last theorem, following the Frey strategy as refined by Serre, by showing that a rho EP as in Frey's construction cannot exist. So starting with a counterexample to Fermat, you construct a mod P Galois representation, you forget about the elliptic curve, and you get a representation of weight 2 and level 2. There's a deep theorem of Maser which will tell you that this Galois representation is irreducible. And we showed that in some sense, one of the basic ideas of a proof is some lifting theorems. You lift these mod P Galois representations to p-adic Galois representations with minimal ramification properties. What we did was we showed that this mod P Galois representation, which is originally arising from an elliptic curve, which might have bad reduction at many primes, actually also arises from a semi-stable abelian variety over Q, which might have higher dimension than 1, elliptic curves of dimension 1. But that has good reduction outside 2 and a semi-stable reduction at 2. Right? So what we showed is that this mod P Galois representation actually lifts to some p-adic representation with the minimal ramification properties. And it arises from an abelian variety which is good reduction outside 2 and not very bad reduction at 2, semi-stable at 2. On the other hand, Fontaine and Abrushkin, I think in the mid-80s, had shown using discriminant bounds and all that and kind of a deeper study of p-divisible groups, they had shown that no such A exists. Right? They had shown that there is no abelian variety over Q with good reduction outside 2 and semi-stable at 2. In fact, I've heard that John Tate in a course he gave at Harvard, and maybe, I don't know, in the early 80s, had suggested that this line of attack on Fermat. Right? Instead of rerouting it to modular form, just try to show it comes from an abelian variety with some sort of very constrained singularities. I mean, bad reduction properties. Right, so this is the proof we gave. In fact, this kind of lifting of a mod P Galois representation to a p-adic Galois representation or an abelian variety with minimal ramification or minimal bad reduction is a key step in our proof of Serre's conjecture. So while this proof, of course, looks different from Wiles, and in some ways it's technically simpler than Wiles because we don't need a lot of the arithmetic geometry which goes into Ribit's like reduction of Fermat to level lowering results of Ribit. Of course, the entire proof of Serre's modularity conjecture really depends very, very heavily on Wiles's breakthroughs, modularity lifting techniques he introduced in the proof of Serre's conjecture, in his proof of modularity of elliptic curves. Right, so in some sense, the initial breakthrough of in our work on Serre's conjecture happened in the fall of 2004 when I visited Jean-Pierre Berger in Strasbourg, and on the first day I went there, we had a proof of the first few cases of Serre's conjecture, right? And because we had two independent observations which we could combine, and we showed that that Serre's conjecture for certain right, that there are no Serre type representations. By Serre type representations, I mean odd, irreducible, two-dimensional model representations. There are no representations of level 1 and weights less than or equal to 8 as predicted by Serre, right? Because there is no cusp form of weight less than or equal to 8. We couldn't do 10 at that point. But, and also we showed that in the weight 12 case, such a representation comes from the Ramanujan delta function. So in the fall of 2004, when we initially started our work, and initial breakthrough, we could prove Serre's conjecture in the level 1 case for small weights by showing there is no such Galois representation because there is no space of the corresponding space of cusp forms is 0. On the other hand, in the weight 12 case, we showed that any representation of weight level 1 and weight 12 comes from the Ramanujan delta function. Right? So the Ramanujan delta function was a key kind of, was one of the first cases we proved of Serre's conjecture. Okay, so this is, he unfortunately passed away a few years ago, and yeah. Okay, so now to end this, I have 5 more minutes, or should I? Yeah. So, so let me end with one small, okay, so this is the Serre's conjecture, of course, I mean, I've told you the story, it's a kind of, Serre's conjecture is now, turns out to be the first case of a series of conjectures one can think about, right? It's just a two-dimensional case over the absolute, over the rationals of something you can think about for higher dimensional cases over the Galois group of any number field. Right, but on the other hand, the classical Serre conjecture is the only known case of that kind of statement. Right, though there have been many techniques which have been developed, and one would think that one should ideally be able to prove more cases of these type of conjectures relating mod P Galois representations to mod P modular forms. Right, somehow this is still the only case which has been proven. Okay, so let me end by telling you one more advantage of interpreting tau p as the trace of Frobenius, right? And how Serre's conjecture plays a role even for that. So for that I'm going to go to this book of Barcy Dixoven and Jean-Marc Couvernier's called Computational Aspects of Modular Forms and Galois Representations, where they undertake the task of trying to find an efficient algorithm to compute tau p. Right, so now I'm going to give you an application of Serre's conjecture when you're thinking about modular forms. Right, so Serre's conjecture is about showing mod P Galois representations arise from modular forms, but they are also useful even if you're interested in just when you start with a modular form. Okay, so again, Barcy Dixon unfortunately passed away very earlier this year. Okay, so for the main result of the book of that book, which is written by several authors, the main result of this book is that the Ramanujan tau function can be computed in polynomial time in log p. Right, so that's one of the main theorems of this book. So surprisingly enough, for this also you can't really just work with the definition of the Ramanujan tau function, right, as this product expansion kind of thing. You really have to use tau p's interpretation as traces of Frobenius in some model Galois representation. Right, so it uses Scoff's algorithm, which he had developed for point counting of elliptic curves, and they kind of generalize this thing from elliptic curves or abelian varieties to higher dimensional, to higher weight modular forms. Right, so let me just briefly explain what they do. Right, so yet another advantage of categorification. It's amazing that the model Galois representation associated to delta helps in computing the Fourier coefficients in an efficient way. Right. So again, if you just try to use the combinatorial definition of tau n, you can compute, right, as Ramanujan did for tau n for n up to 30. But unfortunately, that gives you ways of computing tau p, which will take time like roughly p, right? So it's exponential in log p. But if you really want something which is efficient, you really need to do something more sophisticated, right? Which I find astonishing because I know very little about how one computes really. Okay, so. So for example, the explicit computation of for the explicit computation of tau p, in the book, one really has to compute the splitting fields of the mod L Galois representations, which delta gives rise to. These number fields, which I call K delta L. Right? So for you have to write down, you have to really write down what K delta L is. Right? And for that, I mean, again, you use Serre's conjecture, because what you do, okay, I'm going to skip this. So, in a chapter in this book, the Bosman, one of the authors, writes down explicit polynomials whose splitting field generates K delta L. Right? But for that, so let me tell you this. So these are the polynomials he writes down, right? So these are so this is for K equal to 12 is this weight 12 for the delta case. And I'm just telling you these polynomials he writes down of degree L plus 1, where L is a prime, 13, 17, or 19. Right? He writes down these polynomials, and he asserts and checks that the splitting field of these explicit polynomials gives rise to the K delta L. Right? And how does he do that? But interestingly enough, he writes down these candidate polynomials, but to actually check that the splitting field of these polynomials gives rise to the splitting field, the thing coming from the delta function, he really needs to use Serre's conjecture. Right? Because what he shows is that the ramification properties of these splitting fields of these polynomials is related to things coming from the weight 12 modular form. Right? So somehow you want to prove something, though you're starting with the modular form, to prove that these computationally you've come to the right extension, you really need to know Serre's conjecture. Right? So what happens is essentially one can verify only ramification properties of the splitting fields of these explicit polynomials. And on the other hand, to tie that to the delta function, you need someone to tell you that if you know the ramification properties of an extension, you can show which modular form it comes from. Right? So he writes down candidate polynomials, which of course takes a lot of work, using Arakelov theory and congruences between higher weight and lower weight modular forms. And then he computes Serre invariance, the ramification invariance of this Galois extension. Then he checks that these invariants look like those invariants coming from delta. They have the shape of ramification looks like it comes from a weight 12 form. It's unramified outside L. And then you have to use Serre's conjecture to say that this implies that this field comes from the delta function. Right, so finally, what I wanted to point out is those Serre's conjectures are some converse theorem. You really need it even to prove something about modular forms. Right? So let me conclude by saying Serre's modularity conjecture is used to justify a step in the proof of for p prime, Ramanujan's tau p can be computed in time polynomial and log p. So here one is indeed starting with the delta function, which is a modular form, but yet one needs to use Serre's conjecture to verify the algorithm to compute the Fourier coefficients of delta. Right. So this is one example of the computational aspect. I mean, that Serre's conjecture is also useful for explicit computations. And maybe I think I'll stop here. Thank you.
We use this so people in Zoom can hear us, yes? That is the idea. We could try with a seating microphone.
So the K delta L, weren't they defined in terms of the Galois representation in the first place, or are they defined intrinsically by the delta a priori?
So K delta L is this representation which comes from the GL2FL representation associated with delta. And on the other hand, one might want to explicitly compute them, as they want to do in this book. For that, you have to perhaps one way of explicitly computing them is to try to write down an explicit polynomial of degree L plus 1, which will be some of the action of GL2FL or the projection line of FL. Write down an explicit degree L plus 1 polynomial whose splitting field is K delta L. So that's the task. One of the things you have to do to carry out this task of writing an algorithm to compute tau p polynomial time in log p. What you have to do is try to, the Scope's idea is to compute tau p mod L for small primes L. And use the fact that one knows the bound of tau p, you know that if you know it mod L for enough primes L, you know it. Right? So with the idea that to compute tau p mod L is to interpret tau p as a trace of Frobenius in the mod L representation. And for that, that's what Scope's algorithm does. It gives you an efficient way of computing tau p mod L via this interpretation of tau p as a basis for genius. In the end, you have to write, they want to write down a polynomial and check that it is the right polynomial. And for that, one has to somehow, the splitting field of this polynomial, you don't know that much about it, but you can try to, you can study the ramification properties of the splitting field. And the ramification properties look like they come from the delta function, and hence Serre's conjecture will then tell you that it is indeed constant. So that's the kind of one connection.
Is it known what led Ramanujan to conjecture his upper bound?
Sorry?
Is it known what led Ramanujan to conjecture his
Yeah, this is genius. I don't know. It's a bit mysterious. You go from 6 to look at have an exponent of 5.5 just by looking at these values of tau n for n up to 30. Maybe computed more, of course, but still it seems to be amazing that one would land at the number 5.5 rather than 6. And 6 is very easy to prove, right? You can find a proof with the basic over modular form. 5.5 is much harder. But also, I mean, I think you can explain that. If you look at x squared minus tau p x plus p to the 11, the Ramanujan conjecture, maybe I think perhaps even, I don't know, I've not studied the paper in detail, but you can write down the factorization of this thing, right, of this polynomial x minus alpha p x minus beta p. It's basically asserting that these roots are complex conjugate, and they're not real. So, yeah, I think maybe Ramanujan did, maybe I don't know, something. There might be a better explanation for this, but I don't know what exactly like Ramanujan.
He didn't have this polynomial.
Sorry?
Did he have the polynomial?
Yeah, x squared minus tau p. He does write down this polynomial.
Oh, he does write it down.
X squared minus tau p x plus, I think he will factorize it and does know that this means that the discriminant of this polynomial is less than equal to. I mean, of course, it's conjecture that these roots are never agreed or something. Perhaps such conjecture are not even known in general.
Maybe you said it, but I didn't quite understand the significance of the interest of this algorithm to compute this output.
I mean, because Scope's algorithm apparently is used in every product shipped by Microsoft. Right? If anything of cryptography, I don't know anything about this, but I mean, Scope's algorithm is useful. I mean, I think vast critics and are just interested in because these algorithms were in weight 2 case. When you look at higher weight modular forms, there's no connection with the abelian varieties, and somehow it seems like a different matter. So the book develops the technology to be able to compute these find efficient algorithms, theoretically at least to compute tau. I'm not sure what the
This law, what is the law P kind of thing? That seems really fast for this.
yeah, polynomial time law. The goal was to somehow be able to compute tau p in like polynomial time and the number of digits needed for p. That's some of that was the goal in this one. If you just literally use the definition of the tau p function, or even if you LSC terms, if you want to count the number of points mod p, you need p, not p set because actually p one. But the Scope's algorithm somehow does much better. So they wanted to do the same thing for these modular forms, the higher weight modular forms, the corresponding geometric object is a motive of weight much like 11, 0, 0, 11, so far away from the world of elliptic curves. So they wanted to perhaps show that the theory of modular forms and what is known can be theoretically can be actually used to compute tau p.
So you mentioned that you had your breakthrough on the proof of the conjecture when visiting Berger.
Yeah.
And because you two had separate observations, kind of came together. And could you tell something about the nature of these observations and how they complement each other, or would it be too technical and involved? So?
No, Ramanujan had this kind of, he had observed that if one, he had observed that if you knew something about how to lift Galois representations from mod p to p-adic representations with minimal ramification, then you could get initial cases of assessment. So that was an observation. He also had another very beautiful idea about killing ramification, how to reduce the Z from higher level to level 1. So he had 2 or 3 beautiful observations, and somehow the missing step was, I mean, at least in principle, at least to start doing these literature, you needed to lift Galois representations with to something which is minimally random. So that's something I knew how to do, which I had not published, but I knew that. And so the very first day we met in Strasbourg in 2004, we could do initial case assessment. After that, of course, in principle, there was a strategy to prove all of Serre's conjecture, but it was like you have to use modularity lifting in unknown cases, so it was a technically very hard problem. It took us 4-5 years to actually complete the program, because we improved the strategy and then needed to prove modularity lifting in the right modularity. I don't know, that's it.
Yeah, that was a great answer.
Right, I don't see any further questions. So before we thank our speaker again, I mean, I think many of us are running for dinner at the back. So I think the reservation is at 7, but it might take us a couple of minutes longer to get there. You all know where this is, or perhaps somewhere. How to get there. Okay, so with this, we'd like to all turn us to thanking our speaker again for his beautiful lecture.